Well, hello all my beautiful calculus students. Well, let's venture on to 4.4. I am going to try and convince you of something before I tell you exactly what it is. So up on the board I have two linear functions. One you can tell is v of t, which represents velocity with respect to time, and therefore my x-axis is labeled as time in hours. We have to choose a unit of measurement up here for our velocity. So since we're dealing with hours and you're typically dealing with miles per hour, we're just going to write mph up here for miles per hour. And the example that I chose shows something is moving at approximately 50 miles an hour consistently, 50 miles an hour for, it looks like, 10 hours. Now, something that typically gets kids is they wonder whether or not, or how, you can start at 0 hours at 50 miles an hour without having reached that speed up to a given time period. So what this zero, what it represents is that not that time is zero, well in a sense time is zero, but that somebody has started a timer at that second, and at that second, when they start the timer, when they start recording velocity for whatever this is, could be a car driving down the highway, whatever you'd like to think of it as, whenever they're starting to record the velocity, at the beginning of their recording, the velocity is 50 miles an hour. That's why at 0 I can be 50. I don't have to start at 0 and show an acceleration and increasing. I'm just, 0 is the beginning of my timer. So after 1 hour, I might be going from 1 o'clock to 2 o'clock, or I might be going from 4 o'clock to 5 o'clock. But 1 hour has lapsed, and I'm still traveling 50 miles an hour. Consistently 50 miles an hour for 10 hours. So perhaps I have cruise control on, something like that. Okay, now over there, I have another graph. It has 100, 200, 300, 400, 500, and then S of t. S of t stands for distance. And I'm again dealing with hours, and I just gave you a graph for velocity with miles per hour, so it should make sense that these over here are miles. And I want to see how these two graphs compare, how they relate to each other, and some kind of relationship that we can build from the two graphs. So I'm going to choose a couple of values over here. Let's see, I'll talk you through just a little bit more before we go. If I'm traveling at 50 miles an hour for 1 hour, then I would have covered 50 miles. And over here, when you look at the number 1 for 1 hour, you come up here, halfway between 0 and 100 is 50 miles. If I continue traveling at 50 miles an hour for another hour, so 2 hours total, I would have traveled at 50 miles an hour times 2 hours, gives me 100 miles. And over here at 2, I can see I'm plotted the point 2, 100. So this 100 represents the total distance that I've traveled at 50 miles an hour for 2 hours. I can hop along and just do another check for you someplace later, like at 6 hours. Let's say you travel at 50 miles an hour consistently for 6 hours. Then you should have traveled 50, 50, 50, 50, 50, 50, so that's 300 miles. 50 times 6 is 300 miles. And I come over here at the 6, and I look up to see what's graphed, and this is the point 6, 300. So I'm definitely related. These two graphs are definitely related. I can see a 50 here going consistently straight across, and I can see that this is a linear function, and it's continually going up. It's an increasing function. Let's see, it takes 1, 2, 3, 4, 5, 6 hours to go 300 miles. So 300 divided by 6 is 50 miles an hour. They're definitely related. This is your velocity graph, and this is your distance graph according to that velocity graph. So what I want to show you is this. I'm going to pick a couple of hours over here. I think I'll pick 2 hours. So I'll come up here. And I'll do the same thing over here at 2 hours. I'll come up here. This is the point 2, 100. And this over here is the point 2, 50. And I can pick any other number I want. I'm going to choose, let's go for 7. Do something different here. Give me something nice long thing. It's 7 hours into the trip. I'm still going 50 miles an hour. I'll come over here and I'll pick this 7. I'll erase this 6. So I'll come up here to 7. And what point is here? 7, let's see. Halfway between 300 and 400 would be 350. So 7 comma 350. Now I want you to come up with some relationship of what's happening with the graph between x equals t equals 2 and t equals 7 hours here, and what's happening with the graph between t equals 2 and t equals 7 hours here. So I'm going to give you that relationship. This shaded area in between 2 and 7 would be how much? This distance is 5, and the height is consistently 50. So I'm dealing with the area of a rectangle, base times height. I do base times height, I'm looking at 5 times 50. And that's 250. Now, the 5 was the number of hours. So I'm going to erase this and just write 5 hours. And the 50 was 50 miles per hour. So this is miles per hour. And when I take hours and multiply by miles per hour, my hours cancel, divide off, eliminate, and I end up having 5 times 50 is 250 miles. That should make really good sense to you because we know that rate times time equals distance. The rate we're dealing with in this case is miles per hour. The time we're dealing with in this case is hours. Multiply miles per hour times hours, and we end up with miles. So we can get our total distance, 250 miles, would be our total distance driven between time t equals 2 hours and time t equals 7 hours. That's pretty common sense. If you travel for 5 hours, the distance between 2 and 7 hours, or the time between 2 and 7 hours, if you travel for 5 hours at a consistent rate of 50 miles an hour, then you're going to be traveling 250 miles. Come over here. Can you recognize that 250 miles anywhere? I'm hoping you can. Hoping you can say the difference between this 100 and this 350 is 250. You take 350 and subtract 100, you end up with 250. And this 350, that's a y-coordinate, so that's in terms of miles. And the 100 is a y-coordinate, so that's in terms of miles. You take miles and subtract miles, and you still have miles. All right. So in a nutshell, it works kind of like this. If we find the area under the curve of a velocity function, we have to be talking about a velocity function for this. So if we find the area under the curve of a velocity function between 2 time periods, call it A and B, on some interval AB, that's going to be equal to the difference. See, this minus sign is the difference between the height of the distance function on that same interval. I'm going to write that in mathematical terminology on the board. And it's going to give us this. When we integrate the velocity function, I'm going to use my parentheses first, v of t, with respect to time on an interval from A to B, or in this case, I could call it, and I will do it, I will say 2 to 5. Now this says, give me the area bounded by the velocity curve, underneath the velocity curve, bounded by the velocity curve and the x-axis. Give me the area in between the intervals between 2 and, on the interval between 2 and 7. I don't know why I wrote 5. On the interval between 2 and 7, that's why. And that's going to give me the same thing as this 350 minus this 100. That 350 is the y-coordinate, so it could be thought of as an s of t. However, it would be t is 7. So s of 7 minus s of 2. And this is going to be true when we're talking velocity and distance functions. Let's put it in a more generic format because it didn't have to be my interval between 2 and 7. I could have done 2 and 5. I could have done 4 and 9, 4 and 10, 6 and 8, any interval I wanted. So the interval between A and B of my velocity function is S of B minus S of A. B is called my upper limit, A is called my lower limit. Alrighty. This can be generalized even more if you wanted to back off a velocity function and talk about any function in particular, as long as the function that's sitting inside your integral right here is the derivative function of whatever is sitting over here all by itself. So I'm going to formalize this even a little bit more. I'll bring it into a more calculus format for you, if I will. I'm going to put it right in here. And it's going to say, you can take the integral from A to B of any derivative function with respect to whatever the function is written in terms of. So notice I've switched to x as opposed to t's. And that's going to equal the original function evaluated at the upper limit minus the original function evaluated at the lower limit. Notice that f of b and f of a are both height distances, just like the 350 and the 100 are both heights of the original function. So the area under the curve of the derivative function between a and b is equal to the change in the original function between a and b, or f of b minus f of a. This is known as the fundamental theorem of calculus. The fundamental theorem